Have you ever experienced that strange combination of excitement and dizziness when the plane you're flying in lands at over 250 kilometers per hour and almost immediately comes to a stop? That instant of braking may seem astonishing, but it's the result of meticulous engineering, planning, and procedures that commercial aircraft carry out daily at airports worldwide. In this video, you'll explore the secrets behind the braking of these enormous aircraft, understanding that it's not enough to simply brake like we would in a car, and how the trio of air braking systems, which include spoilers, thrust reversers, and wheel brakes, play a crucial role in deceleration. You'll also observe the coordination required between the pilots and the plane, fascinating facts you'll love, and what happens when something goes wrong during landing. If aviation is your passion, or you're just curious how a multi-ton machine can stop on a limited runway, this is the place for you. Sit back and enjoy. And remember, at the end, if you find this content interesting and useful, subscribe to the channel, like it, and share it with those who want to discover the amazing world of aviation. What speed and weight does an airplane have when landing? To understand how complicated it is to stop an airplane, we must first understand the enormous mass and speed it carries. A Boeing 737, for example, can land weighing around 60 or 65 tons, while wide-body aircraft such as the Boeing 777 or Airbus A380 can reach the runway weighing well over 200 or 300 tons. We're not talking about just any vehicle. These are true colossi. The approach speed, known in aviation as the BREF, is typically between 130 and 150 knots, or 240 to 280 kilometers per hour, depending on factors such as the aircraft model, its weight, and weather conditions. This speed is maintained to ensure sufficient lift, because any lower speed could put the aircraft at risk of entering a STOL stall just before touching the ground. Of course, the higher the speed, the longer the braking distance required and the greater the strain on the deceleration systems. To visualize the magnitude, imagine braking a car from 250 km per hour, a considerable speed, and multiply that by tens of tons of additional weight. Kinetic energy is enormous. Dissipating it in a controlled and safe manner in a limited space is a true challenge in aeronautical engineering. Furthermore, it's essential to consider factors such as slippery runways, crosswinds, snow, airport altitude, and engine power, among others. Any variable can increase the distance required to brake or complicate the final maneuver. Therefore, the ideal landing speed is determined by considering the weight and runway requirements. This way, the pilot can be sure that, thanks to the braking systems, they will have an adequate distance to stop without difficulty. However, many people wonder, why isn't applying high-power brakes enough? Wouldn't it work the same way as in a car? Why can't they just use the wheel brakes? A car, a motorcycle, or even a train rely primarily on wheel brakes to stop. In the case of an airplane, however, this technique would not be sufficient for several fundamental reasons. Immense kinetic energy. At the speeds and weights of a commercial aircraft, the energy that needs to be dissipated during braking is colossal. Relying exclusively on wheel brakes would result in intolerable and immediate heat, which could lead to extreme overheating and a loss of material efficiency, even leading to total failure. Much longer runways would be required. If wheel brakes were the only deceleration resource, landing safely would require endless runways. Commercial aviation operates with runway lengths between approximately 1,800 and 4,000 meters, depending on the airport. These distances are calculated so that, under normal conditions, the combination of several braking systems is sufficient. Residual lift. Upon landing, the wings still generate lift, which prevents the full weight of the aircraft from being transferred to the wheels. If the wheels are not firmly planted on the runway, the brakes cannot operate as effectively as required. Redundancy philosophy. In aviation, redundancy is essential. If a single system, the wheel brakes, were responsible for stopping the aircraft, a failure would mean there would be no alternative. That's why multiple devices are used to help reduce speed, so that if one fails, others can partially take over. Thus, to brake safely and in the shortest possible time, airplanes use a complete set of solutions. Among them, the aerobraking trio stands out: spoilers, thrust reversers, and wheel brakes. Powerful, but not unique. Let's analyze how each plays a specific and complementary role in achieving ideal deceleration. When you're traveling by plane and feel something rise on the wings as the engines make a distinctive sound upon landing, you are witnessing two of the protagonists of this trident, the spoilers and the thrust reversers. Later, more quietly, the wheel brakes come into action. Each plays a role in the braking process of an aircraft. Spoilers are movable surfaces located on the top of the wing. When deployed, they alter the airflow over it and significantly reduce the lift provided by the airfoil. Just as the wheels touch the runway, the pilots activate the spoilers so they automatically activate, generating two instantaneous repercussions. With a reduction in lift, the plane sticks to the ground, transferring its weight to the wheels and increasing available friction. As they lift off, they generate drag, contributing to the plane's deceleration even before the wheel brakes or reversers are fully operational. This sudden change, which can be observed when looking at the wing from the window, is crucial. Without spoilers, the plane could hover for a couple more seconds, making it extremely difficult to stop. The second component of this trio is the thrust reversers, a system that redirects some or all of the air expelled by the engines forward. On turbofan engines, they open with flaps that reverse the flow, generating a force that opposes forward thrust. By changing from forward thrust to reverse thrust, the plane's speed decreases noticeably in a short period of time. This is the rumble heard upon landing, which is different from the usual sound during flight. As the air is diverted, the engine develops a deeper, louder tone. As the aircraft loses speed, its ability to decelerate is also reduced. Upon reaching a moderate speed, pilots typically disengage the reversers to continue braking the wheels. These mechanisms are not present in all engine types. In propeller-driven aircraft, reverse pitch is used, which reverses the pitch of the propeller, fulfilling a similar function. The premise remains the same, generating a force that counteracts the movement and facilitates rapid braking. Last, but not least, are the wheel brakes. They are the final touch that takes the aircraft from an intermediate speed to a near stop. They are generally made of carbon or steel materials capable of withstanding extreme temperatures. The anti-skid system, equivalent to a car's ABS, prevents the wheels from completely locking and skidding, maximizing traction. Many aircraft have an automatic braking function, autobrac, which allows the desired braking level to be set upon landing. In this way, the system distributes the braking force to the wheels according to the selected setting. After an abrupt stop, the temperature on the brake discs can reach more than 800 degrees Celsius. For this reason, extremely durable materials and, in some cases, cooling systems are required. The superb choreography of braking integrates these three components almost instantaneously and perfectly in coordination. First, the air brakes are deployed to stabilize the aircraft. Then, reverse thrust is activated to reduce the aircraft's speed. Finally, the wheel brakes complete the deceleration process until taxiing speed is reached or until it comes to a complete stop on the runway, if necessary. Although contemporary aircraft can automate much of the flight, landing and deceleration are moments where the human touch is critical. Cooperation between the crew and the aircraft ensures a smooth operation. Before beginning the descent, pilots analyze weather reports, aircraft weight estimates, runway conditions, and the type of approach to be made. Based on this information, they determine the approach speed and braking mode, which can be low, medium, or high-intensity auto brakes. If they anticipate a difficult landing due to wind or a short runway, they opt for more aggressive braking settings and adjust the approach using more flaps. Just before landing, the air brakes are primed. So, when the aircraft touches down and the landing gear feels the pressure of contact, the air brakes deploy automatically without any intervention from the pilot at that moment. Once the wheels make contact with the ground and the air brakes perform their function, the pilot adjusts the engine levers to the reverse position, ensuring that the thrust reverse is properly activated. It is crucial to proceed with caution to avoid excessive engine damage. Furthermore, some airports have noise restrictions that may affect the use of reversers. If the auto brake option has been selected, the aircraft will apply the appropriate pressure to the wheel brakes. The pilot oversees the entire operation and can intervene manually, especially if the runway is slippery or if the trajectory needs to be adjusted to stay centered. Occasionally, the captain prefers to apply manual braking from the start if circumstances warrant it or if he or she desires greater control. During the braking phase, the crew communicates to confirm that the systems are operating correctly. The control tower also plays an important role, providing information on runway conditions and surrounding traffic. If everything goes as expected, within 20 to 30 seconds, the aircraft will go from a speed of over 200 km per hour to taxiing speed, ready to head to the gate. This synergy between humans and machines is one of the reasons why flying remains so safe. Pilots undergo constant training to handle complex situations, including emergency decelerations, and planes are equipped with redundant systems to reduce risks. Airborne deceleration is full of elements that are often overlooked by the average passenger. However, it is an endless source of curiosity that reveals the complexity and fascination of aeronautical engineering. In a standard landing, a commercial airliner can reduce its speed from 250 km per hour to taxi speed, which is between 30 and 40 km per hour, in less than 30 seconds and only cover a few kilometers of runway, depending on the flight configuration and conditions. This is remarkable considering its load. As mentioned above, brake discs can reach temperatures exceeding 800 degrees Celsius. This situation is so extreme that if an aircraft makes multiple consecutive landings, especially on short routes or in situations of frequent airlift, additional time may be required for the brakes to cool before its next takeoff. The effectiveness of reversers is clearly felt in the first moments after landing, when the speed is still considerable. As the aircraft slows, the effectiveness of these devices decreases. Therefore, it's common for pilots to disengage reverse when speeds approach 60 or 70 knots, equivalent to approximately 110 or 130 km per hour, allowing the wheel brakes to take over. These mechanisms aren't only used during landing. In mid-flight, they can be partially activated to descend more quickly without dangerously increasing speed. They are known as flight spoilers. You may experience a slight sound or vibration if the pilot decides to use them for a steep descent. Some airports are known for the complexity of their runways, which are short, located at mountainous elevations, or involve challenging approaches. For example, Lukla Airport in Nepal or Paro Airport in Bhutan. In these locations, the combination of brakes, reversers, and spoilers is taken to the extreme, and pilots require special certifications to operate safely. Some manufacturers are innovating with electric braking systems instead of conventional hydraulic ones, which could offer better brake pressure distribution, reduce system weight, and facilitate maintenance. This field represents a promising area of innovation for future generations of aircraft. Some airports have EMAS, engineered material systems that, at the end of the runway, use substances that deform under the weight of the aircraft, helping it brake safely if the limit is exceeded, thus preventing serious accidents. They have proven effective in more than one problematic landing situation. Some people laugh at those who applaud upon landing, but the reality is that, although it is a standard procedure, it is still a critical, complex moment that deserves recognition. It is no coincidence that cheers are heard on some flights, as it is the excitement of watching the plane overcome that kinetic force and secure us safely on the ground. What happens if the brakes fail? Despite all the sophistication, there is always the possibility of failure. Although these cases are extremely rare, aviation is prepared to handle these situations with safety protocols and redundant systems. Many aircraft have independent hydraulic systems, often 2 or 3. If one fails, the others can provide some or all of the brake's capacity. Even if the wheel brakes cease to function, the use of spoilers and thrust reversers provides adequate speed reduction, especially during the initial phase of landing. If the plane loses its braking power, some airports have safety zones or EMAS at the end of the runway. The plane partially stops on this material, reducing its speed by a few meters. If the crew notices the brakes failing before landing, they can opt for a missed approach, climb, and seek an alternate airport with better conditions or a longer runway. Aviators practice in simulators that display brake system, reverser, and spoiler failures to perform optimally in emergency situations. The goal is that, even if one system fails, others can compensate and facilitate a safe stop or recovery. Thanks to these initiatives, serious incidents caused by brake failure are statistically rare. However, the possibility is always considered. For this reason, the aviation industry places so much emphasis on maintenance, pre-flight checks, and contingency plans. Now you understand that braking an airplane, far from simply pressing a pedal, is a complex engineering feat involving aerodynamics, reverse power, and braking systems that can reach extreme temperatures. A couple of seconds separates the plane from 250 km per hour to the moment it rolls smoothly toward the gate. So, the next time you feel that characteristic tug upon landing, remember how much science and technology have come together in those brief moments. And if you're excited to explore these topics, subscribe to continue discovering the fascinating world of aviation, give us a like if you enjoyed the video, and share it with those who might be just as curious. See you on the next adventure into the secrets of the sky.